Okay, so let us begin with today important concept. Another important point here. This is called as critical population inversion. Is said to be critical population inversion. First, we will see this concept orally, that is qualitatively, and then we will go for the next parts as earlier. Okay. Now see here. In earlier discussion, we have in chapter 1 we have obtained one equation. Okay, in chapter 1, okay, don't write here. I just write this for information. In chapter 1, we have obtained this equation for gamma is equal to, if you remember, this is n2 minus n1. n2 is the population in the excited state, n1 is the de-excited or ground state, multiplied by v square into this type of function gv, or this gv is called as, g nu is called as line shape function. Okay, this is nu, this is called as line shape function. So this is what the topic we have discussed earlier in chapter 1, so I am not repeating all these things here. Then this is 8 pi. Now this is nu square, this is v square, this is nu square. V is velocity, nu is the frequency, and multiplied by tau sp. So that derivation we are going to use in this case of critical population inversion as follows. So this quantity, the critical population inversion, we define the quantity. We can define the quantity. We define the quantity. Okay, as I'm writing here, it is depend to be nth. So what is this threshold population density or population inversion, or that is also called as critical population inversion? It is given by nth is equal to, this is simply n2 minus n1. So difference between n2 and n1 threshold. So minimum difference required to carry out this lasing action continuously. Once this action is laser action started, then it will be continuously going on. So to have this type of condition, what is the population difference between excited state and this ground state? That is this threshold value. This is to be calculated like this. So here nth, this nth is called critical population inversion, is called as critical population inversion. Population inversion, or this is also called as threshold population inversion density. Threshold population inversion density. Population inversion density. Actually, as I said, this is a lengthy derivation. We are not going to carry out everything here. It denotes minimum population inversion density required to start the lasing action. Okay, this is minimum. Okay, this is a definition, maybe from the examination point of view. Minimum population density. Population density required for lasing action. Lasing action means it is producing the laser beam. So to require the minimum required population density for lasing action, this is called as critical population density. And here, using this equation which we have written here, I can write. Now look here, in this equation, above equation, there is n2 minus n1. So this factor n2 minus n1 can be written here, and therefore I can write gamma threshold is equal to n2 minus n1 threshold, and this remaining factor is as it is. Therefore, further relation one can write here. This is nth is equal to, now nth, I am writing this gamma th is equal to this n2 minus n1 into th. Then this n2 minus n1 th is equal to nth according to this relationship. So all these factors comes here on the left hand side, or we can change the sides, and the final expression obtained will be look like this: 8 pi into this is nu 0 square, or it is, I think, v0 square. Yeah, nu 0 square, that is the minimum frequency required, that is tau sp. Then it is gamma th that comes from the left hand side, divide by this v square, divide by v square, and here this is delta nu. Now remember, this delta nu and this g nu has one such relationship. This g nu is, this is called as line shape function, which is given by 1 upon delta nu. Okay, so replacing this, I'll get this final expression. N threshold is equal to 8 pi nu 0 square tau sp that multiplied by gamma th upon v square into delta nu. That expression, further solving this, I can write here directly. Further solving this equation, we get final expression as, okay. So in between steps, you can look into your textbook, but I think it is not necessary at this particular time, because we are not going to ask this type of derivations at all. Only its applications and its interpretations, etc. will be asked there, and therefore we finally will get nth is equal to, this is 4 pi into nu 0 square into tau sp multiplied by delta nu divided by this factor is again v square, and this bracket is something L into C divided by capital L. This L is the length of, that means whatever two mirrors we have used, separation between this is this small, this capital L, and then the small l is from this side, whatever distance L we are choosing, this is small l. C is the velocity of light, and all other factors are as usual what we have seen earlier. So this expression tells you the shows that lasing is achieved more easily when this, okay. So this is what final expression for this threshold population density, which is given by this, and here we have to write its interpretation. This equation shows that lasing is achieved, that means laser will be created, laser light will be generated, lasing will be achieved more easily when this RHS, right hand side of above equation, is as small as possible, or as smaller as possible. So we have to make this to be as small as possible, and to achieve critical inversion with the lowest possible pumping power, the atoms must have a narrow line width. So this delta nu should be as small as possible to get this particular value to be as higher as in this case, okay. So in order to achieve critical inversion with the lowest possible pumping power, the atoms must have narrow line width delta nu as possible, and this is the condition, this set the condition on the atoms to be used. So this particular condition is called as critical condition for this is called as critical population inversion. So you need not go into details of that, that is not that important from the examination point of view. So I am skipping this derivation here, which is not needed there. Now let's go for the next point, that is called as condition for steady state oscillations. Conditions for steady state oscillations. So once these oscillations are generated, this oscillation should be there for a longer time, as long as possible it is. And for that, I'll draw one simple diagram to just make you know what this is. This is my cavity where we are having this type of material there. There is one mirror here, which is given to be, this is completely field mirror. So this is the non-transparent, it is only reflective, 100% reflective. This is M1, and on that side I am having another mirror. Now this is partly reflective and partly transmitting. So this is M2, and this is called as an oscillator, optical oscillator, where this cavity is there. This is my cavity, and now once we start these waves here, all these type of signals must have same frequency as shown here. This is my first wave. Actually second wave should be exactly like this. So to get this type of steady condition, what is the requirement of this situation? That is what we have to discuss here. So all the waves are in good phase and there is an amplification too. Okay, actually my diagram is not that good, but you can understand. So all the waves or all the that light that is generated in this particular cavity after this lasing action must be in phase, as well as it must have amplifications, what we have already seen. So amplification is required, as well as they must be in phase. So these two conditions are to be fulfilled. Okay, so I'll write here, it is necessary that it is necessary, in a short paragraph we are going to write this, necessary that, what is this, a wave making a complete round trip, a wave making a complete round trip, complete, I am going to draw another diagram too, a round trip inside the resonator, inside the resonator has to fulfill, has to fulfill a phase condition, a phase condition. That means they all should be in same phase, otherwise that won't be a good laser, that won't, laser action may be there, but that quality of that laser would be not that good if it is not in the phase. Okay, so in addition, phase condition in addition to the amplitude condition, in addition to the amplitude condition, amplitude condition. So both of these conditions are to be satisfied, and here in case of this particular whatever distance we have written here, this distance is going to be capital L between two mirrors. That distance is to be given to be capital L. And remember here, there is one more important point we should understand here. It is necessary that wave returning to some point, that means what wave is reflected at one mirror, now there should be some phase difference, there should be some phase difference, and it should come when it reaches to the second mirror, again it should have this type. So the standing wave patterns, whatever standing wave patterns we observe in sound, similar type of standing wave patterns must be generated. Then and then such type of operations will be useful for our case, and for that particular condition we have to go for this condition as follows. It means that the phase delay between the waves must be same, some multiple of twice pi. So twice pi is the total phase difference, and for a one single wavelength, that's why this should be equal to twice pi. Thus in light, if light starts at a wave peak when it is reflected from the output mirror, it should be again in the wave peak after one round trip or any number of round trips. So trip number one, trip number two, round trips. After every round trip, it should have, if it is reflected in as a peak in the one mirror, so it should be on the other mirror, it should be reflected as a peak. At one, it is at one mirror it is crest, and at one mirror it is trough. That type of reflection is not allowed. If that type of reflection is, then there is a destructive interference. Steady state this pattern, or this what we call standing wave pattern, will not be generated, and in that sense there are certain conditions required. We are writing these conditions as follows. Okay, so for a constructive interference, the condition for amplification is, okay, already we have written this, for constructive interference, and for amplification or amplitude amplification, the condition is constructive interference, the condition is, this condition is a very simple condition, twice mu into L is equal to m multiplied by lambda, where this m is equal to either 1, 2, 3, 4, etc. all the integers. This lambda is wavelength of this light, L is the length of this cavity, and this mu is the refractive index of the active medium. Here this mu is a refractive index of active medium, and therefore this L is the optical path. That means when there is medium of refractive index 1, air is there and we are having L there, then L into this length into refractive index of air is going to be optical path. But in this case, in this active medium, this optical path is given by product mu into L. Okay, that is mu into L, active medium, and mu L is the optical path. Mu L is the optical path. This is the optical path. So these two words must be known to you. Based upon this, so when this condition, above condition, is not satisfied, each wave will reach output mirror in different phases and undergo a destructive interference. So if this condition is not satisfied inside this type of cavity of length L, then there will be a destructive interference. So right here, if this condition is not satisfied, then there will be destructive interference, and hence no amplification of laser light, so there won't be any amplification of laser light. And the cavity length L thus imposes a severe restriction that only those light waves which can fit an integral number of wavelengths within twice the cavity length are amplified strongly. That is very important statement here. We'll write here the cavity length. We have to go one diagram for again here. Cavity length this capital L, okay, capital L imposes an important condition. That only those light waves which, okay, only those light waves which can fit an integral number, of wavelength, within twice the cavity length, are amplified strongly, and other light waves which do not satisfy this condition, these light waves are going to cancel each other. So there is a destructive interference. To have a constructive interference and steady state condition, we require this condition is to be which is to be satisfied. Okay, and waves of all other wavelengths are attenuated. Waves of all other wavelength than this, other wavelengths are attenuated. Attenuated. So that they cancel each other. And therefore we can draw one such diagram here that again makes you clear this particular thing here. So this is one mirror. So draw a big diagram here, or we can draw this particular diagram. This is a mirror. As I said, this is a thick mirror which is having 100% reflectivity and no transmission. That's why this is shown to be something dark as shown like this. This mirror is M1 mirror, so it is completely reflecting the waves. And this second mirror, as I drawn here, this is the another mirror which is a partly reflective and partly transmitting. This is called as output mirror, M2, or sometimes it is called as OM, output mirror. Now in this case, this is the length L, and let's take few simple things here. When m is equal to 1, what will happen? I'll start here and here. When m is equal to 1, we will get this type of wave here. So this waves, this is the its peak, and this wave becomes a smaller wave here. And here when it reflects, the phase difference is as shown like this. So this is called as 2L path. So this wave travels from this mirror to this mirror and comes back this way. So this is called as first standing wave, and this is m is equal to 1. Whereas in m is equal to 2, so this is halfway path. In this particular wave, I am dotted line, this increases, reaches here, becomes 0 and starts falling like this, and again reaches here. So this is having m is equal to 2. Okay, so this is how. And here when this particular wave starts here, as goes this way, and gets reflected here in such a manner, you will get exactly similar wave but of the opposite orientation, and therefore this will reach here. So this is m equal to 2. So this is the standing wave for m equal to 2. See that condition, twice mu into L is equal to m lambda. So in this case it is twice mu L is equal to 2 times lambda. In the first case it is twice mu L into is equal to 1 into lambda. And if I go for the third wave, that is m equal to 3, so in that case you will have, again I can draw this another here, this is up, then down, there are three lobes, up and again down. So this is one wave which is going to be m is equal to 3, and when it is reflected, I'll get exactly opposite wave which goes up, then again down, and then here. So this is m is equal to 3. Now you can understand this type of, what we say, it is called as the standing wave pattern will be generated. So this is the condition which is called as condition for steady state oscillations, and therefore the condition twice mu L is equal to m lambda, this is called as the condition for steady state oscillation. Unless if this condition is not satisfied, then these waves will have destructive interference and no lasing action will be possible, or no amplification will be there. And if this condition is satisfied by this length and wavelength of the light, laser light, in such a case, that lambda is the wavelength of this laser light. If this wavelength of laser light and this cavity length, this particular condition is satisfied, then there is a constructive interference, and then that gives rise to a such type of amplification or steady state oscillations, amplification as well as steady state application oscillations. Otherwise, all other waves which are having length or lambda in such a manner which is not satisfying this condition twice mu L is equal to m lambda, then this type of waves are not said to are not supposed to go for this oscillation as well as amplification. Okay, so write about brief about this. If the space bounded by two end mirrors, if the space bounded by two end mirrors, okay, m1 and m2 mirrors in a laser, is regarded as mirror cavity resonator. Mirror cavity resonator. Mirror cavity resonator. Then the length capital L of resonator should accommodate an integral number of, that is m is equal to 1 2 3 4 etc. number of standing half waves as shown in the diagram. Okay, so this I can write this value for, or the equation for L can be written as L is equal to m lambda divided by twice into mu. So this is called as the resonating length, or this is called as the length required for resolution. of a particular wavelength lambda. So L is equal to m lambda upon twice mu. This is called as condition of resonance. Called as condition of resonance. And if this condition is satisfied, then only there is resonance, there is amplification, and there is a good output of laser. Otherwise, lasing action would be there. But since if this condition is not satisfied, that is, this mu is the refractive index, lambda is the wavelength of laser light, and L is the cavity length. If these three are matching in such a manner, we are getting an expression L is equal to m. M now is 1, 2, 3, 4, etc. Fractional m is not allowed. If m comes in a fractional, that means these three values L, mu, and lambda are such that m comes to be a fraction, then this type of condition is resonance condition is not satisfied. Hence, even though there is a lasing action, there won't be a good output in a laser. So to have a stable, steady, good output from a laser, every time in every laser, this condition L is equal to m lambda upon 2 mu has to be satisfied, which is called as the condition for the resonance. Okay, so this, remember this statement, that this expresses the condition for resonance between the mirror cavity and the light waves of wavelength lambda. Okay, so don't have this misunderstanding that we can produce any laser frequency or any laser wavelength from a given laser tool or laser device. If you have given any HENE laser, for a particular length of that particular laser, there is a particular frequency only which satisfies these conditions, and that's why there is a limitation. Now, in our usual lamp, tube light, or a incandescent lamp, you can have any frequencies, right from 0 to very high frequencies. All frequencies are simultaneously available. That's why it becomes a chromatic source. Number of colors are there. Whereas in this case, we require a particular frequency only, and that will be decided by this mu and L. Mu is the material medium which you are using, and length of that laser, that decides what is the wavelength of that will be generated in that particular type of laser source. So in that sense, this is another important derivation we have discussed in today, that is in the chapter number 3. Okay, and now let's go for the last derivation from this chapter, that is called as cavity resonance frequencies. Cavity resonance frequency. Similar derivation, Maxwell's derivation, plus a second derivation, we'll do that. It is seen, that is, we have already seen in the previous of this section, that cavity will be resonant for those waves which fit an integral number of half wavelength between the mirrors. That means those who are satisfying this condition. The wavelengths of such waves are given by. Okay, now this expression I can rewrite this expression in the other format. The waves, light waves satisfying resonance condition have wavelength. Okay, above expression we have to just write this is lambda m. Okay, a particular is equal to particular wavelength for m value. M is equal to 1, 2, 3, 4, etc. That is given by twice mu L upon m, or like this. When I am supposed to take lambda 1, it will be twice mu L. When I take lambda 2, then it is twice mu L upon 2, that is simply mu L. When I go for lambda 3, third frequency, it is twice mu L divided by 3. So this is 2 by 3 times mu L, and so on. Lambda 4 is equal to twice mu L upon 4, so it is mu L by 2, and so on. So this distance goes on decreasing as we go for larger and larger m. So this lambda m, wavelength of that particular resonating light which is given out in the source, is given by twice mu L upon m. Okay, now this is in the terms of wavelength. Now we know this relationship between frequency, wavelength, and velocity of the radiation. C is equal to nu lambda. So using this relation, C is equal to nu lambda, or lambda is equal to C upon nu, I can replace this equation as follows, and therefore the equation in terms of frequency. Therefore the equation in terms of frequency is, it is given by nu m is equal to mc upon twice mu L, m into C upon twice mu into L. So C is the velocity of light, m is the number which we are taking here, twice mu as usual. It is mu, that is the optical length. Mu L is optical length, 2 is the number comes because of that particular condition. So this is the equation for the frequency. That is what? Cavity resonance frequency. So this is what the above equation. This is cavity resonance wavelength, this is cavity resonance frequency, and that expression for LV that we called as cavity wavelength, cavity resonance length of that particular oscillator, of that optical oscillator. So this equation, and this equations are just same, only first equation is in terms of wavelength, this equation is in terms of the frequency, and therefore theoretically we can go for one, say, small problem here as using certain values. Theoretically the cavity can resonate, theoretically the cavity can resonate, okay, for any frequency at a, can resonate at a very large number of frequencies, at a very large number of frequencies, theoretically, not practically, frequencies that satisfy the above condition, that satisfy above condition, that satisfy above condition. Okay, for example, if I go for the simple example, let's take L is equal to 0.5 meters, that is 50 centimeters. Lambda, if someone takes 5000 angstroms, that is 5000 into 10 raised to minus 10 meters, and a mu, here if one takes a material medium such that its refractive index is 1.5, and if we go for this calculation, if the values are known here, this implies, or this gives you value of m to be very, very large, and this is almost 3 into 10 raised to 6. This m is going to be very, very large. So this entire calculation gives you either this or this. You can use this expression earlier, lambda m equal to twice mu L upon m. Calculate this m, you will get this number m to be very, very large. This is 3 into 10 raised to 6, and it means that the resonator can support, okay, how many? This 3 into 10 raised to 6 different frequencies, theoretically different frequencies. So this resonator would support just a minute, let's take a break, small break. So different frequencies, this particular resonator of length L, for this combination, that means value of L is equal to 0.5, I have prepared a resonator of length 0.5 meters. I have taken a wavelength of 5000 angstroms, and if mu, material medium, is required, which is having its refractive index is around 1.5, then in that case this is going to, theoretically it is going to support 3 into 10 raised to 6 different wavelengths, but this is theoretically. Practically it doesn't support that much things, okay. So this will support these things, and that is how, there is one diagram also we can draw here, but that is, I think this is not needed. So the spacing between the neighboring frequency is constant, as shown in the figure, and I think this is not needed to be taken here. So here this calculation gives you mu m is equal to mc upon twice mu L, and that shows theoretically it supports a lot many number of frequencies, but practically it is not that. Only very few limited frequencies are to be generated in case of laser light. Otherwise this particular laser doesn't work a good laser in this particular case, okay. So to make this small, that means if we want to make this wavelength of this monochromatic, as much monochromaticity we need in our operation in the laser, then this laser becomes a more unstable, or that laser is not that particular good, or laser operation is a bit difficult for us. And if we are making a small bandwidth, that means whatever frequency in wavelength we are getting, if there is some spread associated with that, then that type of laser action can be seen here, okay. So all frequencies can be given. The laser will operate only at a select few frequencies for which gain exceeds the cavity losses, okay. So even though this is the condition, practically we will write last statement here from this particular chapter. So practically practically laser will operate laser will operate only at a select few frequencies for which if this is an important condition, gain exceeds all the cavity losses. So yesterday we have seen there is a scattering, there is absorption, as well as sometimes there is radiation also, that leakage is also there. There are several other different ways in which this particular type of radiations are lost, and if there is loss is there more than the gain amplification, then that means, as I said, theoretically we can have any frequencies there, but for that particular frequency, if loss is more than the gain, then the proper laser action will not be possible. So theoretically, even if we are saying that this particular laser will generate this type of wavelength, but practically it is not possible, because every time to have a practical output for a particular laser, gain amplification gain must exceed all the cavity losses. So this cavity losses are to be overcome by this gain, then and then such type of selected frequencies will be possible. Therefore, it is not possible to generate a laser of all separate wavelengths. That means 5000, 5010, 5020, 5030, all these type of wavelengths lasers are not available. Only selected lasers are available. Because of this practical difficulty we come across when we design these type of particular lasers here. Okay, so here we have finished this chapter number 3. In the next lecture onward, we will go for this another chapter that is called as line broadening of laser wave. So what this concept is, how it comes, what is its practical applications, etc. These things we will discuss in the next lecture. So before we disperse, let me take attendance, so don't go away. Okay, so let's 1 or 2 minutes. So these notes will be again made available to you, very short. Swamini Divya is there, Poonam Tapir, Priyanka Kopade, Pooja Nikte, Monali Devkar, Rutuja Godambe, and Sumit Begde. Okay, just a minute. Stopping the sharing. So let me take the attendance. And now we are going to prepare this attendance. And when we are going to go for some internal marks of these papers, internal mark out of 10. Your attendance will be taken in consideration. तुमच्या attendance ला आम्ही काहीतरी महत्व देणारच आहोत. Okay, so